Hi there, welcome back. So today we are going to be talking about a new kind of test statistic. So we've spent a lot of time looking at quantitative data and calculating Z test statistic and T test statistic. But today we're moving into chapter 11 and we'll be talking about inference for categorical data. And we're going to learn a new test statistic. Now, the structure of a test for categorical variables is the same, state, plan, do, conclude. So we'll still have to state our hypotheses, have some conditions, calculate, and then conclude based on our p-value. But because we're dealing with categorical data, that means that the structure is a little bit different and the distribution is different. Okay, so this is chapter 11, section 11.1 on chi-squared. All right, so either you have printed out your notes or you are taking your notes on a separate sheet of paper. You're going to need your calculator today, and I'm going to be using the table of values just to show you where you can find this new distribution. Okay. So we're going to talk about the chi-squared tests. Now there are 3 different chi-squared tests, and it's all dependent upon what kind of data you're given or how the data has been collected. And so the main thing to know is that chi-squared tests, there are 3 types. We'll talk about the first one today. And what it is, it's inference for categorical data. So categorical data is data that we can arrange in not always a two-way table, but oftentimes a two-way table. Today we're going to look at a one-way table with our goodness of fit test. Now, before we get started, we need to talk about what is this new distribution. It's called chi-squared. Now I know it looks like chi or chi, but it's the Greek letter chi. So I don't know how you want to chi. I don't know how you want to phonetically write that, but it's chi-squared. And so what chi-squared is, it's a measure of mismatch. And one thing to note is that we have no chi-squared confidence intervals, only tests. So that's good. So we only get to do a test here. So we don't have to learn different procedures or different conditions because you can only do chi-squared tests. Okay, so the chi-squared distribution is like the T distribution. It's a family of distributions that depends on the degrees of freedom. Okay, so just like the normal curve and the T distribution, it's a density curve, and it's a family of density curves where the area underneath is equal to 1. Okay, now what's different is because chi-squared, it's being squared, that means that the axis always starts at 0 and chi-squared is always positive because you're going to find chi and then you're going to square it. Sort of. You're going to find the value of chi-squared. So you'll see that there's a square involved in the calculation of chi-squared, and so the answer has to be positive. Okay, now you may notice here that we've got some right-skewed distributions. So the shape of chi-squared distributions is skewed right. When the degrees of freedom are small. But just like the T distribution, as the degrees of freedom increase, then we approach normal. Okay, now the degrees of freedom depends on the type of test. So for the goodness of fit test, which we're going to talk about here, for goodness of fit test, the degrees of freedom is just n minus 1, where n is the number of categories. Right, we're dealing with categorical variables, so how many categories do we have? For next time when we talk about homogeneity or independence, it's going to be degrees of freedom is the number of rows times the number of columns. Right, so we'll talk about that more next time. For today, we're going to use the goodness of fit test. Okay, and so before we get to that, I just want to illustrate here that what's happening is we have, as the degrees of freedom are increasing, the shape of our distribution is starting to approach normal. Okay, so we've got this first one here, degree of freedom is 1. That's this curve, so really right skewed. But even as small as going to degrees of freedom of 4, we start to see this bump up here. Now we're still really pretty right skewed. And here's degrees of freedom of 8. So if I have a larger sample size, then I'm going to approach normal. Now, I do want to point out table C. So table C is where we're going to be looking in the table for the chi-squared distribution. It says the table entry for P is the point at chi-squared with the probability P lying above it. So it's just like table B, the T distribution, where the area in the distribution is above. So they'll give you the little picture here to remind you of that. And the way you read this table is just the same way that you read the T distribution. So upper tail probabilities are on the top of the table, and you go down degrees of freedom to find the chi-squared. So chi-squared are all the values that are inside the table, okay, just like we had over here in the table B. Now notice at the bottom of the table C, there are no confidence interval values because you don't make confidence intervals with chi-squared. Okay, so our main focus today is to talk about the first kind of goodness of fit test, which some of you may already have some exposure or experience with because you've maybe taken AP Bio. So this is the chi-squared test. So the chi-squared test for goodness of fit is called, sometimes we abbreviate it, the GOF test, or GOF. It means goodness of fit. So what we have here is a single sample, and we have one categorical variable that has multiple categories. I'm going to show you how to use your calculator, but if you have an older calculator, an 83 or an 83 plus, the calculator doesn't have the capability, but you just use some lists and you can find the chi-squared value. So it's not like a huge detriment that if you don't have 83 or 83 plus. If you don't have it on an 84, you just need to update your operating system, and then you should be able to get the goodness of fit test. Okay, so what we're trying to do here is to use it to help us determine whether a population has a certain hypothesized distribution. So we're going to be told some information about some distribution, either from a hypothesis or from some historical data. And we want to see if the distribution in our sample has changed. So what we do is we are calculating a quantitative measure of the extent to which the observed counts differ from the expected counts when the null hypothesis is true. So the object is to determine if a population distribution has changed, and then chi-squared is a measure of how much the sample distribution diverges from the hypothesized distribution. Okay, I know this is the first time we've talked about this, and so it sometimes feels a little bit overwhelming. Essentially, we have some hypothesized distribution, or like I said, we have some historical data that we're looking at, and we want to see if that distribution has changed. And so we'll take a sample, a current sample, and then we'll be able to compare it to the distribution previously, or what our hypothesis is. Okay, so the conditions are not going to be out of place, I would expect. So the conditions are, we need random. All right, so we need a random sample from the population of interest. Okay, I'm hesitant to say or a randomized experiment because we just have a single sample. It's very rare that we would have an experiment for just a single sample. So I'm going to leave that bit off. Remember that the 10% condition is here. If we're sampling without replacement, then we need to check the 10% condition because of our independence violation. So we want to make sure to check that. And then we use a large counts, but this large counts is not like it was before. Okay, so this is written this way: all expected counts, and that's the same thing as expected values, are all greater than or equal to 5. Okay, so what is this about? So we're going to have some observed counts. This is going to be from our data. And then we're going to have what's expected. And so expected is based on our hypothesis. Hypotheses, actually. Okay, now you have to be really careful here because it's counts. We have to make sure that we are not using percents, not percents or proportions. So sometimes students will get an error because they will have put in the